Okay. So today we will go through two topics. First, Matplotlib, which is the plotting toolkit that is kind of de facto standard for MATLAB-like plotting in Python. And the second part will be on a special tool called Paraview, which is a user interface, graphical user interface for scientific visualization. And I will go through how the tool works, and the second part of that we will go through how to generate data that you can actually use in that tool, and how you can take your own data and import it into Paraview. So, but first with Matplotlib. So Matplotlib is a plotting library that is a module for Python. If you have installed Anaconda, it's built in, and it provides you with there are two interfaces. There are one really advanced interface to Matplotlib that has an object-oriented design where you can really go down low level and do plotting. But there is also one that is perhaps the most used one. It's an interface to plotting library that provides similar commands that we have in MATLAB. So you probably recognize, if you have used MATLAB, you probably recognize how the plotting command works. So how to use Matplotlib. So this command here is just for when you're running a notebook and you want to have the figures in line with your code. Otherwise, the real command for importing it, or the way you do it usually, is to import Matplotlib pyplot, which is the simplified interface to the plotting library, and you import it as PLT. You will see a lot of examples on the web that uses the same kind of convention to import. So Matplotlib pyplot as PLT. And it's really easy. So Matplotlib has a plot command for plotting really simple diagrams. And the simplest one you can do is just providing a list with values. And you do, after you have plotted, you do show. And this is, if you're working with Notebook, it's not strictly necessary, but if you're working with Matplotlib standalone, if you run it on the Python command line, you need to do show to kind of bring up the window with the plot in. So if we run this here, I need to execute them in order. This. Now you see it creates a plot like this. So in this case, it just assumes that the order is 0, 1, 2, and 3, and just plots them out and draws lines between them. Also, it's not strictly necessary to have arrays with NumPy. Matplotlib can be used just with lists. That works as well. But you can also plot NumPy arrays. So in that case, we need to import the NumPy library. And what is beneficial is when you plot is to provide an X series and a Y series. And in MATLAB, you do that by specifying 0, colon, and then a step size and the end value. When you're using NumPy, it's a good idea to use the command linspace to provide a starting point, end point, and the number of points you want to provide. And then we can use the feature of NumPy that it can calculate a function over an array and return a new array with the computed values. So if we look at this here, you can see here we have two ranges here, and the Y here is the computed values. You could have done something like this, but it's not recommended because it's not always sure that you get the last number here. So linspace is a better way of using to create series that you can plot. And then we can plot the function, plot the series here by specifying X and Y. So X is the X series and Y is the Y series. And this is very similar to what you get in MATLAB. So MATLAB has a plot command as well that does the same thing. And you will also see here there are similarities to MATLAB here. You can do X and Y, and then you can specify that I want red circles here. So red and an O for a circle. And then you can add a dash here, then you get a line between the circles as well, like this. And B here is for blue. So this is the MATLAB syntax for specifying the graphs here. And if you want a dashed line, you can do double dash here. That will be a dashed line. And you can have plus signs as well. And you can have green pluses with line between. So there's a lot of combinations here that you can do to create the plots you want. So if you're running a notebook here, or I don't know if you have, you can try this out yourself here. But I will, hello, is it compute course? Yes. In this case, I want to plot the f of x, sin 3x divided by 3, sin 5x divided by 5. And then this is the way you do it. You create an x series here for the range. I have 200 points here, and I calculate np.sin 3 by x divided by 3, and so on. And then we plot this like this. So you can use, the important thing is that if you do this, you need to use NumPy to kind of get the functionality that it computes for every x value and y value as well. So you need array features of NumPy to do this. Another often thing you want to do is have multiple series in the same plot. In this case, you need to have multiple y series. So in this case here, I have x is the same, and divide range here, and then I create an x, y1, y2, and then I have the different functions that I want to plot. And then I just add them in triplets, you can see there. So you have this is the first series, and this is the second series. So this is the first part, and this one. You can have different parameters for the different plots as well. I need to execute my code like this. Then there is a lot of properties attached to every plot, and you can modify those either by specifying the parameters. Here you can look in documentation here. There is a API documentation. All the parameters you can set. So there is, for example, an attribute here called line width that controls the line width of the lines being drawn. And in this case, this will change the line width of all the series that you plot. So in this case, all of them will be a thick line like this. It's also possible to change the individual values for every series, but then you need to get the objects back from the plot function, and that is perfectly possible. So the plot function actually returns the series as objects that you can manipulate. So in this case, I have two series here, and I can assign them variables here, line 1, line 2, and then I can manipulate the properties of each of these here. So line dot 2 dot. Okay, if you run it in your code example, you will probably get a lot of method that you can call here. So here I can set individual line width for the different series here because I have access to the different projects, different objects of the series. So now you can see one is thicker than the other one. It's also possible to get, so lines here will actually be a list of line 2D objects. And then you can use the setP function of the Matplotlib interface to actually set properties on multiple series at the same time. So this here sets the property line width of all lines here. So it will have the same effect, but now it's at the same 8 on every one of them. Then you can also plot to multiple figure windows, and it's a bit hard to see here in when you're running a notebook. But if you want a new figure, a new plot that is standalone from another one, you start by specifying plot figure 1 and then plot figure 2. That will kind of switch between the different figures you want to plot to. And when this command here will plot to figure 1, and this will plot to figure 2. And in this case here, we'll just get 2 figures on top of each other here. So, but if you run this example here, I can show you here. So I will copy this over. I paste them in here, but now I also have to do import number as LP. And I need to get the functions here as well. So if I run this now here, let's see here, run Python 5. You can see here now I have 2 separate figures. So Matplotlib can be used either as in a notebook, but also standalone. And that's why you need a show, because show will bring up the windows and the execution of the code will stop here and until you have completed it. So if I close that one and I close this one here, you can see the code terminates there. So you need show when you are running it standalone. Sometimes you want to have multiple plots in a single, multiple views of a function in a single plot. And to do that, you use the subplot command, this one here. And the syntax for that is a bit odd because you give a number here, actually an integer, that with 3 numbers here. So I would say I have 2 rows with 1 column. So in this case, those 2 first, the 2, 1, that is 2 rows, 1 column. And I will plot the first column here. So the last one is the actual figure or subplot I want to use. And then this is 2, 1, 2. This is the second plot here. So if I run this, you can see you get them. This is the first, so 2 rows, 1 column. This is the first plot, this is the second plot. You can do the other way around, you can subplot 1, 2, 1. Then you can have them 2 columns instead. So if I run this, I will get this instead. Something you always need to do is to decorate your plots with titles, headers, labels, and stuff like that. And it's also very similar to MATLAB. So in this case here, if I want to provide an X label, I just call plot X label. Y label, same thing here. And here you have the second plot here. I have a Y2 label there. And then you can see here that I have labels here now. shared label here. So it doesn't provide a label here because you have a shared series here.
You also share the ticks and the numbers or letters or whatever you have in the X.
So you can blend them.
Can you merge the two figures so that you also share like the values of them?
Yeah, so you remove those.
Yeah.
I'm not super expert in Matplotlib, but I imagine you can. But I can show you here in the beginning here, there is very good documentation of the different plot commands. And so I give you a high level overview, and then you have to dig down yourself. There is so much in this API. One cool feature with it is that you can actually use LaTeX commands inside the plots. So if you want to add text to your plot, but you want to use a mathematical function, you can do that. You need to specify a raw string here because you are going to use backslashes inside a string to specify the formula here. So this is the math command in LaTeX. And here you can also specify the centering if you want to center the text somewhere. So you will set the text in actual coordinates of your diagram. So this will put the text at pi divided by 2 and in the y direction 0.8, centered around this point. So if I run this, you can see here that it actually provides you a formula directly in the plot. And it's positioned in the coordinate system of the actual series here as well. And you can see that it's centered around this point. And there are several other things you can do. You can change the properties. So this was a text, the text command that only provides the text. You can also put arrows in the text, so you can put an arrow and an annotation to that arrow. So here I have the text max. I have the XY position. I have the XY text. So it will draw an arrow from the text to this position here. And here you can set the color of the arrow and also change the size and also center it. So in this case, it will create an arrow that starts from this position here. And so this is the text position and goes to this position here where you want to point to. So in this way, you can actually do annotations directly in the diagram. And I can change the size here as well. Okay, I didn't know. Actually. Okay, it makes make the arrow a bit smaller on the. Let's see. Yeah, I leave that to you. But it's a way of annotating directly in the plot. You can also set the axis limits by using the xlim command here. So we can zoom in here, going from 0 to m pi and limiting us in the y direction to 0, 1. So now we have this point here instead. You can also change the scale of the axis here from linear to logarithmic here by specify y scale or x scale. So I'm plotting an exponential function here that plots like this. Then I'll just go through some of the other parts here. It's better, there is on the web page, there is tons of examples of plots. So if you want to plot something, I recommend that you go let's see here. So if we start with Matplotlib here, there is a gallery section, I think. Yeah, it's under my Zoom thing here.
It's also in the cheat sheet.
Yeah, here. So just to give a visual, you can just browse here to something that you want to plot in a similar way, and then you just go into one of these and you get the example. So I would recommend doing this and looking in how they do that. Now you know the kind of basics, how to get a plot in Matplotlib, and then go here and find the thing you want to plot. So there's a lot of different plots you can do with Matplotlib, and I won't go further because I would like to continue with the Paraview stuff instead. But it's very similar to Matplotlib, very easy to use. You can also do 3D plots like this here. And in one of the user interface exercises, we will also use Matplotlib as a control into the user interface. So you can create user interface where you embed Matplotlib inside. So you can create a user interface where you can do a very simple graph plotter using this tool built into Qt. So you can integrate it on web pages and in user interfaces as well. So let's switch to Paraview. So Paraview, I will go. Oh, I forgot. I have this one here first. So a short introduction to what Paraview is. So this is a slide that is available on the Kitware web pages. So Paraview is an application developed starting in 2000. Also has a couple of years on it. It gives you an overview of what Paraview is and also large-scale visualization. The Paraview is an open source application. It's multi-platform, so you can download it for Mac, Linux, and Windows. It supports distributed computation. So if you have really large models, you can actually run it on multiple processors to do the visualization algorithms. And it's open, and you have it's a very easy to use user interface. However, this slide is intuitive. Yeah, when you know the flow, it's intuitive, but it can take some time to get over the basic user interface of it. But I will try to explain it here in this lecture. So scientific visualization. This is typical things what you can generate with Paraview. So you can visualize streamlines, you can visualize finite element models, you can visualize molecules, dynamic stuff as well. So you can not only do static visualization, but you can also do visualization of dynamic data. It's very popular. It has been downloaded several times, and it's still used on the largest systems in the world for doing visualization. These are old data, but you can see that it can handle quite large data sets without any problems. So the architecture is shown here. We are going to use the Paraview client. But it consists of several parts. This Paraview client is a user interface. There is also a Paraview Python, which is a dedicated Python interpreter with the built-in library of Paraview. So you can use all the functions in PV-Python. And I will also show you how you can use this to create, you can do visualization and generate a Python script, which you can modify yourself later on to do your own visualization. Paraview, there is a web-based toolkit. There is also standalone version of Paraview that can be run without user interface to do in situ visualization. So you can submit that with your computational job on our clusters, for example, to do the visualization at the end. And you can also build custom application. It's built on top of Qt. So Qt we will learn for Python as well. So it's implemented in the Qt user interface library. And it's built on top of a server that you run when you start the Paraview client as well, but it's not so interesting for this course. But VTK is interesting because Paraview builds on the visualization toolkit, or VTK. And that's a C++ library for visualization that contains almost all scientific visualization algorithm into a single library. And that library builds upon OpenGL for hardware accelerated graphics. It can use MPI for doing the visualization algorithm. For example, slicing of large models can be done in parallel. And it has some other libraries here as well, but it can take advantage of modern visualization technologies as well, from a laptop to a supercomputer. Started in 2000. It's a collaboration with American labs here, so Los Alamos National Laboratories, Sandia National Laboratories, and AC. So it has been developed for many years, and you will see. I will show the application here how much it supports in different algorithms and file formats that you can read in. So, what is visualization? Yeah, this is kind of the essence of it. So you have your data that you have generated, for example, in a simulation. It can be data from sensors or something, and you want to make sense of this data and produce something that you can interpret as a human being somehow. And so going from numbers to a plot or a graphics that you can interpret yourself. So Paraview supports a number of different data types that are kind of the primitives of the visualization. And so you can have uniform rectilinear data, basically rows, columns of bricks that you can visualize data in. And data can be located both in the cell, at the surface. You can provide data, so field data in each node of these cells, and you can do different things with those. So you can have multiple fields in a data set that you can visualize in different ways. Non-uniform rectilinear, then you have bricks that are spaced on with different densities in different directions. Curved linear, when you have something that has a rule that it bends the same structure. You have same row columns and depth here, but you give it the curve as well, this rotates around some kind of axis. You can have very generic data, polygonal data. Polygons here that is connected together, typically finite element meshes. You can have unstructured grids that basically you can have different elements types that are connected together without any structure in that sense, but they are not connected to each other. That is more, there's relationship between the elements. Here is kind of non-relationship. Multi-block I haven't done myself, so I have used all of these here. There is also a lot of tutorials on the web. So Paraview is free, but they want you to buy this book. It's a very good book in how you do scientific visualization. There's a lot of tutorials on the web. The web page has excellent documentation as well. So I will, instead of doing the slideshow now, I will try to do a live run of Paraview. So I'm currently running remotely here on Cosmos, which is our new computational resource. So I have started Paraview through our desktop system here. So you can, if you go to the applications here, you can go to visualization, and you find Paraview 5.11 here. And if you start that, you get a small dialog box here where you can ask for how much time you want to use it. And in this case, it defaults to the A40 nodes that we have. A40 is a graphics card, similar to 4090 graphics card. And then you start it and you get it will run on a backend node with a graphics card, and then you have Paraview running here on the desktop. So the user interface is divided in, you have the toolbar area here, where you open files, you control the models, you have some view controls there as well. On the left side here, you have the pipeline browser. Here we will load our data into Paraview and apply filters and operations on the data. So, and it will all flow from the data sets through the filters into the view here. So this is the view area where we look at the data. Then you also have a properties part here, which is where you can set the data of the different filters, the different algorithms, but also on the data set itself, and change the different parts here in the pipeline browser. So if you click here, you will be able to modify the operations here. The user interface is very flexible, so you can change the layout in different ways. You can. There are also a side window coming up here if you in other ways here. So what I'm going to do now is artificial example here. So you have sources here that can generate different kind of data. So you can add, for example, 3D text and stuff like that. But I will add just a sphere here. So this is a constructed example here. Normally you will load your own data in here, and that will be the source. But now I have a sphere. You can see here, by default, nothing happens. And because Paraview mostly handles large data sets, it's not always beneficial to kind of just display things, because it's could be large models and it can take time to draw. So the default action in Paraview is to load it, but do not display it yet. So you can see here that the apply button here becomes green. And that means that it's ready to display itself if you want to press apply. But you have the opportunity here before you display it to actually change the parameters here. So here you can see different radius and stuff like that. And you can change it here, and then you press apply, and it will appear here in the viewport. So now you can zoom in, you can rotate. And you can see here that it's a bit jagged. So I can add resolution here to, that is the number of segments here. So I can do 16 by 16. Press apply again, and you see it's a bit smoother. You can also change the representation here. So by default, it's a surface rendering. The representation mode can be changed here. So you can set, for example, wireframe, and then you can see how the mesh is actually constructed. You can set surface with edges, then you can see the surface, but also the edges of the mesh. You can do surface. You can also do point, so you can see all the points. We will go with surface here. You can also see here there's a quick change here on the top here where you can do the same operations here. You can also set the colors here. So the solid color here you can change here. So by default it's just gray, but you can change it here by pressing edit. And we can do a red one here. Okay. You can see it becomes red. You can also make it more shiny by using specular here, pulling that up. You can see that you get a more shiny sphere like this. You can make it transparent as well. And all of these properties here apply to everything you'd load into the model. You can modify these parameters as well. You can also provide an axis here, so you can see the size of the thing you have created. You can do you can also change the radius here if you want to have a bigger sphere. Like this. So this is the very simple sphere that is kind of illustrative. So what we're going to do now is we're going to start from the beginning. And this program doesn't have a new, it has a reset. So if you want to start from the beginning, you have to use this arrow here that is called reset session. So are you sure? Yes. And now we are back in an empty session again. And what we're going to do now is we're going to load a model. If you look here, files of type, you can see here that it can load a lot of different file types. So it has support for a lot of different visualization types. Sorry?
DDB files.
Let's see here.
Protein data.
Yeah. What's it? Type. The question if I create a new, just a test here.
Yeah.
If they're okay, good. So I'm going to load a model, and there are some example models that you can experiment here in the example session here. So I will use this one here that is cylinder that is heated up. I will this. So you can see here now I've loaded a model. And you can see inside the model here which data fields are available. So this is the ones that we can visualize. And you can see there are node properties. So you have there available on the edges here, or the nodes of the elements. So you apply, and now you see it loads it in, and it just visualizes the geometry here. There is no, it's just a cylinder. There is a heater here inside the cylinder, and there is a volume here that's been heated up. So let's see, go a surface with edges. You can see here the mesh of this. And the first thing I'm going to do is what we can easily do, we can go into the properties here and say here, so it says solid color here, but here you can actually select what I want to visualize. So let's see, we visualize the temperature. You can see it colorizes by the temperature, and you get automatically a scale here. That is the max and min temperatures. So the problem we have here is it's a bit hard to see through the model. So what we can do then is you can look at the toolbar here. You have the most common operators here that you can use on your visualization here. You can contour, you can create contour lines, you can do clip, slice, the single plane, and then you can do threshold, you can do glyphs, and you can do stream tracer, warp by vector. So warp by vector, if you are in mechanics, for example, you have a displacement field, and then you can use warp by vector to actually display the warped structure. It will move all the nodes by the vector, the deflection field. But we will use the clip here. So if I press clip, you can see here that you get I have photos now with my rotation now. So you get a clipping plane, and you can move this clipping plane in different directions like this. You can also, if you want a bit more control, there is you can set the origin, you can set the normals here. You can also have predefined clipping here, X, Y, and Z like this. So let's go there. And you see here that apply here is not, you haven't done anything yet. And also you can see here that when I created this operator, it added itself to the pipeline. So I started with, this is the data set. I added the clip operation here, but it's still not visible here. So if I press apply here, you can see here that it splits it open like this. And you can see inside the volume now. And now you also see that the original data set, it's not visible here. So you can press here outside, there's an eye to actually display the original data set as well. What you can do with this is if you turn that on, and then you go down to the properties here, go to opacity, and you lower the opacity here, you can see the total volume here as well. So this way you can hint to the actual volume here. We can add axis here as well. So you can see where we are. You can also, if you're kind of get lost here in the view here, there is always these here on the top here. You can do reset. Okay. Then it will kind of move it to the center again. There is let's see here, zoom to data. That is also to, if you're zoomed out somewhere, you can always press this here to fit in the window. You can use the zoom window here if you want to zoom in on a detail here. You can just zoom in like this to look at it, and you can go back again here. You can set the different axes here and different views like this. So you have many opportunities. So now I want to, so there is also a vector field in this model here. So I want to be able to see the flow. What I can do then, I want to show the flow in the entire model now. So it's very important where you do this here, where you start the operations here. So if I do create flow lines now and have this clip selected, the flow lines will only be computed on the result of this clip operation. So we only get flow lines in half of the model. So I want to create flow lines in the entire model, so I have to go back to this one here. Also, I want to turn off the, let's here use. Show plane. I can remove this here, so I don't want this operator here to be shown in the visualization, and I can just unclick it here. So I go back to this data set here, and now I will use the stream tracer. And I want to use, let's see here, you can see here vectors here. I have a flow field, speeds, vectors, and here I can show the algorithm for producing the flow lines. I would like to release the flow lines in a point cloud here. So I, not on the line, but from this sphere area here. And I want to make it a bit bigger here. So I do a bit bigger for. That. And then see what happens here. So now you can see here that there are flow lines visible now here. To make them show a bit, I can now they are colored by temperature, which is perhaps not what I want. So I can do color flow lines that are just white, like this. You can also color them by the speed here. And I can make the clip here a bit transparent as well. Hope you can see them. So make them even more visible. What you can do, so these are now drawn with single lines, so just wireframe, really thin lines. But you can actually create something, you can let Paraview do, create a three-dimensional tube around these. So what we can then do is I will check the stream tracer, make sure that it's active. Then I go to filters. And here is the different operations. So I've shown you the clip and also the stream tracer. Those are only two of the many hundreds of filters you can apply to a visualization. So if we go down to alphabetical, I think they almost can't fit the screen. So here you have the different operations that you can do on your visualization. What I usually do, if you know the name of a filter, you can instead go to search, and then you just start typing here, tube, and it finds a filter for that. So let's do the tube. And here you can set properties here, the radius. You can also vary the radius on different field types. If there is a arrow with two arrows in a circle like this, it will create the default value for you. Look at the data and see what could be useful here. So let's do apply. And now you can see you've got three-dimensional streamlines. And you can do, let's do this more specular here. So they are a bit shiny. You can also perhaps change the, so for the 0 point. Like this. And you can, of course, change the color scale. And I missed to explain that, but you can, every color scale here. So in this case here, to differentiate the colors here between the temperatures, I can press the edit button here. Then you get the color scale editor here, where you can edit the color scale. You can do that manually, but you can also press the heart here, the favorites presets here. You can also do the presets here. So let's press the presets here and do another color scale here. Now you can see that the streamlines are colored differently now, but the temperature scaling is the same. See if we can do. Then we press clip here. Another thing you can do is display the actual vectors of the vector field. So let's turn off our streamlines, go back to the original here data set. So you can see here that you get this tree here. So this count goes to the clip. So this is one trace of the streamline, and then this stream tracer goes from directly to this source here, and you have the tube that goes from the stream tracer. So you create this flow here. So let's go back to this one. And we can turn that on like this. And then we do glyphs here. So glyphs can place symbols at different locations in the vector field. So then we have to specify which array should orient our vector symbols. So we use W here, or V. We scale it with the V here as well. And then we do an auto scale here. And let's see what happens here. Apply. So now you can see here I get arrows that are scaled in the orientation of the vector field. But now you can see also it uses three-dimensional arrows, and that can be quite computational heavy if you have a large model. So what you can do then is you go into the glyph type here and you select arrow here instead. No, sorry, 2D glyph. And apply. Then you get line arrows here as well. You can also control the amount of arrows you want and how they should be displaced. So in this case, it displays them uniformly around in the entire volume. You can also all points. Then you get arrows in every point on the data set. You can set every nth point, so every, let's see, fifth point. And you can have uniform distribution, and then you can say how many sample points you want. Only want 2,000 here. This. So when you have a model like this, what you can do in Paraview now is you can save it as a state file. So if I go in here and do File, Save State, you can save it in a special file format called Paraview state file, but there is also an option to actually save it as a Python file. So let's do test.py. Yeah, yes. And then you can select what you go into it like that. And if we go into you can see here that it generates Python code. And this Python code you can run using the pvpython command of the Paraview toolkit. So I can show you here, if I close this and I do reset here. Go back here, load state. We go to the test.py here. And I'm back. So what this done, it actually executed that Python code and created the model again. And it loads the file. So this is a file reference here to an external file. And the state file is basically just operations needed to come to this visualization. Yeah, you can edit it in VS Code. You can run it without Paraview, but you need to have the pvpython interpreter. So if you on these systems here, I think you can open a command line prompt on a Windows machine or Mac machine and type pvpython if it's installed. If you load a module on the Aurora or Cosmos system, you can type pvpython and it will display the visualization. Then it will display it without the user interface as well. So you will just get a window with a visualization. So that is a good tool. So I think we'll take a 10 minutes break now, and then I will go through how you can get your data into Paraview as well. Let's start again. So now we have a nice tool to visualize our data. So now we need a way to get data into the tool. the default file format of Paraview is the BTK file. And we have a library in Python that we can load using pip that is called PyVTK. And it's not a graphics library, it's just a special module to generate VTK files in a structured way. And VTK file supports all the files that you have in Paraview. So you have image data, you have rectilinear grids, structured grid, unstructured points, you have polygonal data, and unstructured grids. So all of these you can generate with this PyVTK module. So you install it using pip install PyVTK. This is just an example file I have downloaded here that we're going to use as well. So ignore that for the moment. We can use PyVTK using from PyVTK import star. We can also import PyVTK as VTK. That's also fine, but I've been a bit lazy here. So what you need to do when you work with this example, work with this library, is that you need to create structure. You need to create all the different data types that you need to go into the data. So first you define a structure. So you have points and polygons here. So points, so this is the kind of geometry of the mesh. And the polygons points to these data points here. So we have 0, 1, 2, 3. So this is the points 0, 1, 2, and 3, and so on. Then you have to, so VTK and Paraview stores, if you have the mesh, you can attach data to points, to cells, and the data can itself be scalar, there can be vectors, and everything. So you can attach these fields to the points. And here you can see I create point data here. I create a new object with point data, and inside this I add scalars. So in this case it's 0, 1, 2, 2, 7. That will be scalars attached to these points here. And then I can name them as well. And that is really a good idea to do this, because that is the name that will appear in Paraview as well. So if you open the file, you can find the fields that you have defined by naming them here. I can also have cell data. That is data attached to the element in the model. And here you can see I attach scalars, I attach normal, and I attach field. So cell IDs here, I give IDs to the cells, and I also go face attributes here. This is not so common. And also, so scalars and normals are not rarely used. It's scalars and vectors that you add. So let's see here, if I do this here. And then I run this here. So then finally you create the VTK file here by creating a VTK data instance that where you combine the structure, the point data, and the cell data. And you can write the file as a ASCII file or a binary file. And you determine what to load here by specifying ASCII or binary here at the second parameter. And we can look at the file here. So this is the typical VTK file. It starts with VTK data file version 2. There is, you can specify some text here, what format it is, ASCII here, and then you said dataset polydata. Here's points, integer type, and then you have polygons, and then you have cell data, and so on. So this is the standardized file format. So what this module does is make it easier for us to handle it in Python and generate it automatically for us. So let's see if we can read that file. So I will go into here. And I need to download this file here. So when you're in a notebook, you can go into the file section here, and then you can download a file. So I have downloaded a file here, and then I can open my VTK session. Let's see. go off full screen. I go back to Paraview and I do open. And I think it's in my home directory, downloads. Here I have my VTK file open. So here you can see I have a cube. You can see here I have my sample scalars. Those are the ones that are attached to the nodes here. And you can see they're interpolated over here. And if we go in here, I think this surface with edge is a very nice tool to see when you are debugging your inputs here, how it looks. So you can see it's a surface model consisting of triangles here. And we have data attached to the nodes, and you can see data is from 0 to 7, which also seem to fit what we have generated in our file. So let's go here and do a reset. Back to our book. Then you have structured data you can create. So in this case, I have do very quick. So I do structured points, and here you have 3 by 4 by 6. This is the number of elements in the different directions, X, Y, and Z. And then we just attach point data to all of our points here. So here we have, in the order they come, so 0, and then just fill it up here with points, the values here. And you can see it's scalars here again. And then we write it out here. And then we should have an example 2 here. Download that. This is something you will see also if you name files in with numbers, you can let Paraview load all of them together in a single data set, so it groups them together. But in this case, we have just example 1 and example 2, so there are different meshes. So we need to open it up a bit here. Apply. Now you see you get an empty box like this. We go in and surface with edges here. So you can see here now we have 1, 2, 3 here, and we have 1, 2, 3, 4, and in the C-axis we have 1, 2, 3, 4, 5, 6. And then we go in here and we see here, if you don't name your scalar values, it will automatically number them here. So you have scalar 0, that is the first scalar field. And now you can see here, it colors it with the colors of those nodes that we have here. If I had used did here, you can always have name. You can name anything here, and it's a good idea to do that as well. We can also do a combination here. So let's keep our structure. So BTK data, we will only, let's see here. Yeah, we have example 2 here, and we load example 2, and we will only load a structure here. And then we will provide, we have a function here with X, Y, Z. And then we append data to this here. We add scalars, and then we add scalar field X, Y, Z, computed by the F value here. So this will use the function here to compute the values of each point here. So it loads the structure here of this field, which we saved here. And then, but it just loads it. And then we can add point data to this here, append, and save it out to file again. So let's see here if we can go back here, download. And we go back to Paraview. Reset again. So not too much difference from the last assignment here. We go in representation, surface with edges. Now you see here, we named our field the x times y times z here, so it's very easy to find. And you see here, it calculates the colors depending on the x, y, z coordinates. And here is a similar way you do provide a different scalar field again. But I skipped, this is also interesting here. We'll go to this one instead here. So you can create unstructured grids as well. And here we have defined points and vectors. And then we can combine these together here. So you can create something consisting of multiple different data types here. So you can do points, hexahedrons, tetrahedrons, polygons, triangles, chord, triangle, line, and vertices. So you can combine them together here to create an unstructured grid. We can attach point data and here we attach a vector fields, this one here. And then a scalar field just with a series of numbers here. And we load this one here. So you can see here that I have different element types just combined in a mismatch here. And they are colored by a range here from 0 to 27, which is 0 to 26. So, but what I also can do here, which is not shown here, there is a vector field here as well. So we can do glyphs here, attach them to the vector field here, scale by vectors, scale by size, and then apply. So here you can see the vectors that we have to the different node positions as well. So in the next example here, I will use more realistic data. So I have a data file, UVW, which I will download here. And you can see here it is as a header like this. And there are data here just separated by spaces here. And you can see that the variables are X, Y, and Z and UVW. So this is a vector and the other ones are points. And you can also see that there is you can see the structure is 96 by 65 by 48. So we will use a function in NumPy called load.txt, which is a very fast routine for loading loading arrays from files. And we don't want to load the first two lines because they are header of the file. So we can do skip rows 2 and just load the rest of the data. Next, we need to separate our points and our vectors, and you can use that using array notation here. So we take all the rows and 0 to 3 of the columns here. So 0, 1, 2 to the points, and then we have all the rows, and then starting from 3 going to the end is our vectors. One problem we have with the, I'm not sure, it could be that it's fixed now, but that the PyVTK does not support arrays. So what we do here is there is every array object in NumPy has the ability to convert itself to a list. So we can go to list here will return a list of our points instead. So next we will create our point data here, and we create a vector field, add our vectors, we name them vec1. And we create a structured grid here. And now we need to see the columns here, 96 by 65 by 48. So we create a structured grid, attach our points and our point data. Then we write them out to a file called UVW, and we create them as ASCII. So let's run this. So we have gone from a data structure we have read in, for example, from a measurement site, and then we convert it to an array, and then we convert it to the data structure that is required to create the VTK file. So let's see here if we have this file, VTK here, yes. So now we download that file. And we go back to Paraview. So we have a block here. Just do surface with edges here. So now you can see here we have a volume with vectors on each point. And it's some kind of calculation array here. So we probably want to, we can just see, just plot the, do that. We can color by the absolute value of the vectors here, and we can remove the edges here. We just plot the surface. So now you can see here that we have, what we're plotting now is the magnitude of the vectors on each point. So you can see the speed is varying. We can probably do a slice here in the middle. We do. See inside here. But I think the better thing is to do streamlines here. So let's do, make the opacity, make it transparent like this. And then we do streamlines. Or filters with a tube. Just a bit big. Here we can see the streamlines. We can also do glyphs. Here you can see the arrows here, and we can do them color by, so you can see them all. And of course also combine them if you want. So now we have gone from a table of data to a visualization of data. And there are some, you can also animate this if you want, but I don't have time to show you this today. Like that. So let's do a reset. So then the last example, or next last example here is a elevation file. So it's an image file containing elevation data in grayscale. It's a special file, so we know that it's binary, so we need to load it with RB here in Python. And we also know that there is a header section here that is 268 bytes long, so we move our file pointer a bit further into the file, and then we read from file. So there is a from file here, and we have to specify here to NumPy what data type it is. And in this case, the data type in each grayscale is unsigned bytes. So we tell Python here, read in an array that is of the type unsigned bytes. So it will, so NumPy will read this and interpret it as unsigned bytes. We print out the shape here to see how it looks. And then we know that the file is also 400 by 400. Let's just download it here. And when you load it in like an array, it will be a long array of data. So we need to be able to visualize it and export it. We need to reshape it to the actual size. So in this case here, we do 400 by 400. So we create an array that is 400 by 400. We don't do any copy here. We have all the data. We just reinterpret it as 400 by 400. And we do a plot here as well to show what we have read in. Then we do export it, create the point data here. We provide our X value here, create structured points here, 400 by 400. So it's a two-dimensional grid. We attach our point data to this grid, and then we export it to a file, ASCII here in this case. So let's see here what it looks like. So you can see here that seems to be correct here. We have something that looks like elevation data here. You can see here that is 160,000 bytes. And you see that is 400 by 400, 160,000. So that works out. And now we are creating an elevation file here, hopefully. Elevation BTK. So now we will see if we can visualize this elevation data in Paraview as well. So let's load. I didn't download it. So let's do it. Just apply and see. So okay, so now it recognized this as a two-dimensional. So by default, it is just an image here. So we need to switch from a two-dimensional view to a three-dimensional view here if we want to work with this. So we have a flat surface here. If you want to visualize a flat surface and make it three-dimensional, we can scale it. So let's see, we go search, warp by scalar. We don't have a vector field. You can see here that the data if we have data for a vector field, we could have warp by vector here, but we only have scalar data here. So warp by scalar, and you can see here they have a scale factor you can apply. So let's first compute, use the normal data in the data sets to calculate a reasonable scale factor, and then we apply. You can see here that it applies a scaling factor. But you can see here that it's not quite smooth. And that is something we need to fix. So the first thing, we have to convert it to surface. And then we need to Generate surface normal. So if you look, we can zoom in here again and look at the model here. We hit the surface wireframe here. So to compute the lighting here, by default, it just computes the normal of a single surface. And that means that you get this faceted lighting. So what is missing here is that you need to compute the lighting, the normals for each node point of the mesh, and you can do that by using the generate surface normals. And if you apply here now, you see here that it smooths out. And now we can also do it more plastic here as well. And we can, of course, change our like this. So now we have gone from a binary file to a three-dimensional file. And this is you to be able to do the generate surface normals, you need to have a surface data type. So this is just a extra step that shouldn't be needed, but you have to do it to kind of go from one data type to another data type. So to be able to generate surface normals, you need to have a surface, and you don't get a surface here. So that's why you create a surface with this special filter here. So, final example. So Perlin data, now you can also visualize the volume data in Paraview. And to illustrate this, I have just created a function here to generate Perlin noise in a 128 by 128 volume. And then I create structure point and attach data to that. So let's see here. And then we do in 3D there. No, it don't. There we have it. So this is a bit larger file. So let's download. It's a cube, should be. And then we do, I usually just do this surface with edges. You can see that we have loaded everything. So you can see it's a cube with a lot of cells in it here. So there should be, if we do an axis here, 128 here, yes, seems to be correct. So let's hide our edges here. Let's just do coloring by scalars here. So you can see here that it's a random field here, or volume field here. What you can do here, simplest way is using the contours here to plot the different values here. So let's see if we can do zero value. So you can see here that the range is from -6 to 6. So if we plot the 0 value here, and then we So we display the surface where the value in this volume is 0. And then we will apply. So now you can see here that you get a surface here where the value is 0. And we can, of course, color it by, oh, now it's 0, yes. So so there is a 0 value here. But we can add more values here, so we can do 0.1, do minus 0.1. Then we can get more surfaces in this one here. But we can also do volume. We view it as a volume here. So let's turn this on here again, and then we switch to volume. Yes. And now you can do edit. So you can make it see through here depending on the values you put into the scaling here. And this is done on the GPU on this machine here. So let's see if we can do it better. Now you can do different here. You can do ray traced volumes here as well. Not sure if I can. So good. Something else. This is something you can try out as well. If we go back to normal surface here. So by default, Paraview uses OpenGL for rendering graphics here. If you want more realistic rendering, you can actually go in here, enable ray tracing. So you can actually render this ray traced. And let's see here, we can do. So you can get shadows. You can do different passes, ambient samples too. This is just that it is reasonable fast here is actually because we are running on a full 48 core node now. So it can do almost real time on CPU. So this is CPU based ray tracing. So when we switch to ray tracing here, it's running only a CPU. So when we turn off ray tracing, we have GPU based graphics. But you can turn on to generate images. If you want to get better image, you just can add ray tracing here. And then you get shadows and all that stuff. So that's possible. However, it costs a bit in CPU. So that is what I wanted to show, basically how you can work with this application and how you can get data from Python into Paraview. And also that you can run it on so this is running on Cosmos Live. So it's real-time rendering on the graphics card on the backend node of this compute node. Any questions? I think it's fun when you get your data into Paraview and you start to experiment with it. It's really fun. Also, be careful with the color scales because the human eye is sensitive for colors. So it's good to choose the default color scales and not invent everything yourself because it's those are kind of proven color scales that are built in. So it's good that the lecture is almost over. Yeah. So that was what I have to do today. So I will stop